Hello, welcome to Deterministic Optimization. My name is Shabir Ahmed. I'm one of the co-instructors of this course. In this lesson, we're going to continue our discussion on modeling with binary variables, and we're going to observe how to model some non-convex sets using mixed integer linear constraints. Notice that I've highlighted linear again just to make sure that we do not introduce nonlinear expressions in our formulations. So let's start with a very simple class of non-convex sets. So in particular, the domain of a discrete variable. So a discrete variable, remember, is a variable whose domain is an element of a discrete set, a finite set. So in other words, x, our decision variable, is supposed to be a member of this finite set, a1, a2, through ak. So how can we model this particular non-convex expression using linear inequalities and integer variables? Well, if it turns out that a1, a2, and ak are contiguous integers, for example, if this was 3, 4, 5, and so on, then we can model this as a simple inequality on x. X is between a1 and ak, and x is an integer, right? So we could simply, in the example what I just said, 3, 4, 5, and 6, we would just simply write x is between 3 and 6, and x is an integer, and x integer. That's what this symbol means. And that would have been a correct model for this non-convex set. Again, we have linear inequalities, and with the integrality restriction, model this non-convex set. If these are not contiguous integers, for example, if we want to model x is an element of, let's say, 2, 4, and 7. So how do we model this? Well, these are not contiguous integers, so we can model this simply as, we would just model this as x is equals to 2 times y1 plus 4 times y2 plus 7 times y3. That's what this expression is overdoing. And then we want, of course, that y1 plus y2 plus y3 is equals to 1, and y are binary variables, right? All of the y's are binary variables. If y is a binary variable, only one of them will be 1, and x will exactly be only one of 2, 4, and 7. That's what this notation is telling us to do here. So those are simple ways of modeling this particular class of non-convex sets. So now let's talk a little bit more involved non-convex sets. So here we have a semi-continuous variable. What is a semi-continuous variable? A semi-continuous variable has a domain which is a union of intervals, right? So x comes from L1 through the interval L1 through U1, union with L2 to U2, union with LK to UK. And we are going to assume that because these are intervals, the bounds, L1 is less than or equals to U1, U1 is less than or equals to U2, and so on. So how do we model this? We introduce one binary variable, let's say yk, to denote which interval you are on. There are k intervals, there's one binary variable per each interval, and they sum up to 1, which means that exactly one of those intervals will be turned on. All the other intervals will be turned off. And once we turn on an interval, it has an associated continuous variable, zk. Once yk is 1, zk is a number between lk and uk. And so if I turn on a yk, that interval will be active, and all the other zk's will be forced to 0. And x is just written as the sum of those zk variables. So let's just do an example just to be kind of thorough here. So we would like to write I want to say x is between 1 and 3, let's say, and between, let's say, 8 and 10, right? So how do I do that? So I can write x is a number between, let's say, z1, is the sum of z1 and z2, and z1 is a number which is y1 and 3 times y1, and z2 is going to be between 8 of y2 and 10 of y2, and we also add the constraint that y1 plus y2 is equal to 1, and both y1 and y2 are binary variables, right? So exactly one of them will be 1, and the one that is 1 is going to turn on the corresponding z variable. The other z variable will be set to 0, and it will model correctly what we are intending to model, which is that x is the union of these two intervals. Okay, so suppose now we want to require a slightly more complex situation where we require that x satisfies one of the following k systems of inequalities. So we have a several systems of inequalities, ak, x less than or equals to bk. Here A is a matrix, x is a vector, bk is a vector. And suppose that each of these systems define a polytope, that is a bounded polyhedron. Then a formulation for this system is we're going to introduce a new variable uk, which is a clone or a copy of the x variable and corresponding to the kth system. We're going to introduce a new binary variable yk, which tells you which of the systems are going to be turned on. So here's yk. So sum of the yks should be equal to 1, and yk is a binary variable. You're going to satisfy only and exactly one of the systems. And whenever you satisfy the system corresponding to that, there is a uk variable. ak uk is less than or equals to bk yk. If yk is equals to 0, it turns out that because it is a polytope, uk will be equals to 0. And if yk is equals to 1, uk is allowed to be any variable that satisfies the systems, and corresponding x corresponds to that particular setting of the uk variable. Let's discuss this in a little bit more detail with an example. So here is a simple example in 2 dimensions. So we have one system, x1 plus x2 is less than or equals to 2, which is that constraint. x1 is greater than or equals to 0, which is that constraint. x2 is greater than or equals to 0, which is that constraint. So this particular system defines this polytope, this blue polytope. And in the second polytope, we have x1 is between 1 and 3, x1 is between 1 and 3, and x2 is in between 0 and 2, which is between 0 and 2. So that defines this red polytope. And we are interested in modeling the union of these two sets, which is this non-convex object over here. So how do we go about doing this? First of all, let me write all of these inequalities in less than or equal to form, just to fit in the format that we have just discussed this. So notice all we have done is just negated the inequalities which are greater than or equals to and written them in less than or equal to form. That's the first step. The second step is now we are going to introduce variables corresponding to each of those 2 different systems. Now remember, here we are going to use, so when you see a subscript, so x1 is the first component, and the superscript denotes which of the 2 different polytopes you are on. So x1, the first component of x1, is written into 2 parts, u11 and u12, where u11 corresponds to the first polytope, the x component of the first polytope, u12 corresponds to the x1 component of the second polytope. Similarly, x2 is written as u12 plus u22. Again, so this corresponds to the second polytope. Okay, so pardon me, there should be a 2 here. This should be, I should correct this. So this is the second component, so this is the second component, and this should be a 1 here. So that's the correction. So now what do we have? So we want to write u11 plus u21, because we are talking about the first polytope, is less than 2 times y1. u12 is less than, and then you have u11 is less than or equals to 0, which corresponds to this constraint, and u21 is less than or equals to 0. Similarly, from this constraint, you have u12, which corresponds to the second polytope, is less than minus 1 times y2, the first constraint. The second constraint is u12 is less than or equals to 3 times y2. This constraint is u22 is less than or equals to 0 times y2, which is 0. And the final constraint is u22 is less than or equals to 2 times y2, which corresponds to that constraint. And then again, you want y1 plus y2 is equals to 1, y1 is binary, y2 is binary. Once we do that, so notice that, so we have, then this gives us a right formulation for the set that we would like. Now notice that we have been making use of the bounds on the variables to develop these formulations. In general, it is impossible to develop correct mixed integer linear formulations without bounds on the variables. If there are no bounds, we will impose large artificial numbers, sometimes called big M numbers, as variable bounds. So let's do that with an example. So here is a specific set, non-convex set that we'd like to model. So we are interested in modeling the set of vectors in Rn such that which is sometimes called the zero norm, but it's called the cardinality norm, is less than or equals to k. So here k is an integer between 0 and n. And this symbol, this modulo x with the 0 subscript, it means it is the number of non-zero components of x. So what are we interested in? We are interested in the set of vectors x in n dimension such that it has no more than k non-zero components. Let me tell you why this is a non-convex set. So let's talk about n equals to 2 and k equals to 1. So in other words, we are interested in the set of vectors in 2 dimension, which has at most one non-zero components. So what are those vectors? So if I draw the components, so this vector turns out to be, so these are all the sets which are here. So these are all the vectors which has x0 to be 0, x2 to be 0, and these are all the vectors which have x1 to be 0. And so clearly you can say we are interested in those, the set composed of all the vectors in this, in the shaded black area, and that is a non-convex set. Okay? So now notice that this set is not bounded. So we are going to impose some bounds. We are only interested in the components xj which are between some numbers minus m and plus m, where m is a large number. So now we can write down a mixed integer linear programming formulation. We just write xj is in between minus m times yj, and xj is less than m times yj. Yj is a switch, it's a binary variable, which turns on which component is allowed to be non-negative or non-zero, right? And of course, we can only allow k of them to be non-zero. That's what this constraint tells us. And if you just stare at it for a minute, you'll realize that this is a right formulation for the problem at hand. Okay, so let's summarize. So we just saw some examples how to model different types of non-convex sets using mixed integer linear programming. Now it is again important that these sets are modeled to that we would like to model are bounded, and so sometimes we need to introduce artificial bounds, and also it is very important to make sure that the resulting formulations are linear. All right, we'll pick up in the next lesson. See you then.